So this is the wafer we're going to start off with. So it was a blank wafer. When I'll show you the blank wafer, we buy these wafers in cassettes like this. So this, initially the blank wafer looks like this. There's nothing on it. It's just silicon material. On the silicon I did a CVD, chemical vapor deposition of silicon nitride, and that was done. And then chromium was done, and then followed by aluminum. That's our starting material. All right, so here's a spin coater. Spin coating is, I showed it to you last time, is a very, very simple but very effective method. All right, so the wafer is placed on the chuck and it's held by vacuum, and it spins. And you want to center it so it doesn't fly off too much. There we go. Okay, so I got photoresist here. Alright, so I'm going to dispense some photoresist. And the spin starts, so there it is. So most of the photoresist is actually thrown out. It actually ends up wasted. That's one of the drawbacks of spin coating, but the upside is that it produces very uniform coatings with very little effort. Okay, release the vacuum. I can pick up the wafer. So there it is. Obviously you don't see the resist, it doesn't stand out that much because it's very thin. It's about 1.5 microns thick. The background is of course aluminum, so it looks like it's aluminum, but there's a slight tint suggesting there is something on top of the aluminum. It's not that obvious. But once you do the lithography, it will become clear that you do have the material on it. So once we've done the spin coating, the next step is to drive off the solvents. The solvents, the majority of the stuff that's in this photoresist is solvents. Only a little bit of that is the photochemical. So we got to remove the solvents because the purpose of the solvent is to make it spin coatable. And that's, since that has been done, I'm going to drive off the solvents, and the way to do that is by baking it. You just put it on a hot plate at a predefined temperature for a predefined time. Hot plates, we use many different temperatures, that's why we have several hot plates. So bake it for about 90 seconds. Okay, so I got a clock running here for 90 seconds. Yeah, sure, go ahead.
When you put the nitride and the chromium and the aluminum on there, how did you place them on the wafer?
Okay, so the question is, how did I do the nitride and the aluminum? All right, hold on there. So the nitride was done with the chemical vapor deposition method, which is, I might have briefly shown it last time in the next door room. It's a mixture of silane gas. Silane contains silicon and hydrogen. No, this bake is done. Let me get the wafer out. So all right, we're going to let it cool off here. So we mix silane and nitrogen in a plasma, and then it'll decompose into silicon nitride, and you form silicon nitride. That's actually one of the best way to produce silicon nitride, because you can adjust the chemical composition to get the correct stoichiometry. Because if you want to do aggressive etching, the one we're going to do is pretty aggressive etching. You got to etch through 500 microns of silicon. You need a very robust mask. So it was done through CVD, chemical vapor deposition process, the silicon nitride. The chromium was deposited through evaporation, electron beam evaporation. I showed that equipment last time as well, where you heat the chromium and let it evaporate in vacuum. And then the aluminum was done the same way. It's electron beam evaporated aluminum. Is that what you were asking? So the photo mask is right here. This is the wire pattern. It's printed, it's plotted on a glass plate, and it's transparent, except for regions where you don't want to be exposed. That's the wire pattern. So the wires are black traces and the rest of it is transparent to ultraviolet. And we're using a mercury lamp, 365 nanometer mercury lamp. So the sensitivity of the photoresist is for that wavelength, 365. So I'm going to put the mask on there. So this mask is also held by vacuum. I got to make sure the vacuum is on. Yeah, vacuum is good. And flip it. I always get concerned when I flip it. If the vacuum is not on, the mask will fall down. Alright, and then we lock the mask in place. So the mask is held rigid. It's not going to move. Only the wafer underneath it is going to move. So the wafer goes on the bottom plate. So it'll be facing up towards the mask. So I place it and engage a vacuum. So load, engage a vacuum. So the vacuum holds it. So while I slide it in and out, it's not going to slip around. And then it's actually an automatic process. So what it's doing is going to raise the wafer up towards the photomask, and it's going to do what's known as a wedge error correction. They're saying performing wedge error correction. That's basically, if you got a mask here and the wafer here, they got to be perfectly parallel. If there's some kind of wedging, a tilt between the two materials, the mask and the wafer, you have a gap, and the gap is not even. So it's one thing to have a gap, and it's even worse to have an uneven gap. So it's just creating an even gap, and now I can expose it. I don't need to align anything yet because there's nothing on the wafer. It's just blanket aluminum. So the next step is where I align for the next mask. So this one I don't have to align, so I'm just going to go ahead and do the exposure. The lamp is running at 20 milliwatts per square centimeter. That's the intensity of the lamp, and that's being pre-calibrated. And this photoresist requires a sensitivity of about 300 millijoules per square centimeter. And that's something that we have to routinely calibrate. We got to check the photoresist, how much energy does it need to expose. This is about 300, 250 to 300. So since I'm running at 20, I'm going to do an exposure. I can adjust the time. So I'll put it to 15 seconds. That'll give me 300 millijoules. Okay. And I don't need to align. I'll show you the alignment step during the next one. So during the exposure, this is the lamp housing. The lamp is actually in the back. There's a 1,000-watt mercury lamp. The lamp housing comes forward, and there's a mirror here and a shutter that turns the beam on, and you'll see it. There it is. There's the UV. It's being exposed. You're not seeing the UV. You're seeing the other wavelength of the mercury lamp. Some of them are in green, and that's what you're seeing. So the clock is running, and it'll automatically close the shutter, and the exposure is as simple as that. It only gets tedious when you have to do alignment, which you'll see. So it's exposed. Of course, you can't see anything because nothing has been processed, so it looks just like when you put it in. So now that the exposure is done, there's another big step. So I'm going to put it on a hot plate again. So back to the same hot plate, 100C, 90 seconds. So I can program in what developer to use. So this is a developer. The developer for this photoresist is tetramethyl ammonium hydroxide. It's known as TMAH. Highly dilute. It's like a soapy solution. And that's the bottle here, and it's fed into the developer, and this wafer will spin. So I'm going to mount the wafer on the chuck. It's just like the spin coater, except here it's spinning and spraying at the same time. All right, and it's held by vacuum. And close this. Make sure the water is on. I know you can't see through this. It's not very transparent. Now it's done. Get off the vacuum, and now I can release the wafer. I can see some traces. I don't know whether you can. It's very faint. So I'm going to put it on a microscope so you can see it. Before that, I'm going to blow dry it. So I'm going to go over to the fume hood here and get rid of all that water. Now I'm blowing it with nitrogen. It's not compressed air, because compressed air is not clean. Compressed air contains moisture, it contains oils from the pump and so on. This is coming directly from liquid nitrogen, so it's ultra pure nitrogen. It's a little different from this tool here that we looked at last time, which is the evaporation tool. Here, a material is heated with an electron beam, and then it's evaporated due to the heat. So I pointed out last time, we have material in crucibles like this. This is actually tungsten oxide, so we place the material in here, and then it's heated with an electron beam to evaporate it. That's the cathode. So I'm holding up here the cathodes that I installed here. This is the cathode. On the cathode, we install a disc of copper or aluminum or whatever metal of interest is installed with these rings. So it's got to be the right size. It's got to be a 3-inch diameter and a specified thickness of, I think it's a 1/4 inch. And this whole head is referred to as the cathode. This is the plasma gun. This stays inside the vacuum chamber. So part of this whole shaft, part of it is in the vacuum. So anything below this is in the vacuum. This is outside, so you can feed power to it and water goes through it. So what happens inside the vacuum is that then we flood the chamber with argon, high purity argon. The reason we choose argon is inert. It's not reactive, and it's also a fairly high atomic weight. So what happens is that the argon, it'll ionize. So unlike the previous example, we are using this for deposition. Deposition of thin films that are used in MEMS, in micro electromechanical devices. Some of the thin films that I used are silicon nitride, silicon dioxide,